In this section of 873, we will finish our discussion of J models with how you deal with seasonality. BJ techniques can also be used in the situation where there is a seasonal component. Notice that the model is broken up into a trend piece and seasonal piece. This is no different than all of the other techniques that we have seen. The seasonal component is deterministic with periodicity S. The trend piece is stochastic and is modeled utilizing the ARIMA techniques. We already know that a series that exhibits seasonal variability is not stationary. We will need to create a stationary series in order to use the BJ techniques. This will be done using seasonal differencing. The first seasonal differences is found by taking the present observation and subtracting the observation in the same period during the time period before the present time period. In the case of a seasonal model using ARIMA, we will have orders for the seasonal piece, PDQ, along with the non-seasonal orders, PDQ. Let's look at the monthly average air temperatures for Nottingham Castle from Jan 20 and Dec 39. Use this data to create a stationary time series. Here is the series. Notice that this is monthly data. What is the seasonal length? Here is the plot of the series. Let's look at the ACF plot. Here is the ACF plot. Notice that the maximum lag is 5. The actual maximum lag is 60, but the plot has been created taking the seasonal lag into account. Breaking the ACF plot into the separate components is necessary so that we can assess the orders for each component. Here is the seasonal component ACF plot with the maximum seasonal lag of 12. You should note from this that the seasonal component is not stationary based on the slow die-down behavior of the ACF. Since the seasonal component is not stationary, we need to create a stationary series by taking the first seasonal differences. In this case, the seasonal period is 12. Here is the first seasonal difference series. This series seems to be stationary. Let's look at the ACF plot. Here is the ACF plot for the seasonal difference data. From here, we can see that this series is stationary from a seasonal perspective. Now, what about the non-seasonal component? Here is the ACF plot for the difference series. This plot shows the entire series. You should be able to see this by the fact that we have that large ACF value at lag 12. There seems to be a cutoff for the first 6 or 7 lags after lag 2. Let's get a closer look at this. Notice that at lag 10 the ACF starts to get large again. This should not alarm you. This kind of thing will happen as you get close to the seasonal lag. Based on the lags that we see just after lag 2, it seems that the ACF plot does indeed cut off after lag 2. We can conclude here that the first seasonal differences are stationary in both the seasonal and non-seasonal components. In order to identify a model, we will need to create a stationary time series in both the seasonal and non-seasonal components. It is usually easier to work with the seasonal component first. This is because it will affect the ACF plot for the non-seasonal component. Once we determine a stationary series, we use the specific ACF and PACF plots to determine the orders for the seasonal and non-seasonal components. Here is a review of the rules to decide on the type of behavior for each component. Once we determine a model, we will take care of model fit, adequacy, and forecasting in a similar manner is on the non-seasonal case. Let's decide on a model for the Nottingham Castle series. The sample ACF plot for the seasonal component seems to cut off after lags 1 or 2. The sample PACF plot seems to exhibit die-down behavior. Based on the sample ACF and PACF plots, it would seem that the seasonal component exhibits either MA1 or MA2 behavior. The sample ACF plot for the non-seasonal piece seems to cut off after lag 2. The PACF seems to exhibit a die-down effect. Now, some would argue that this could actually cut off and the other plot could die down. Let's try it both ways and choose the best model. Which model you choose is based on your point of view pertaining to the non-seasonal component. If you think that the ACF plot cuts off after lag 1 or 2, then the behavior is MA1 or MA2. If you think that the PACF plot cuts off after lag 1, then it is AR1. You also assume that the other plot dies down. Let's take a look at our list of model candidates. We have 6 possible model candidates. Let's compare each one using the AIC criterion. Here is the comparison for Model 1 versus Model 2. Based on the AIC, Model 2 is the better model. Now let's look at Models 3 and 4. Here are the results for Models 3 and 4. Model 2 is still better than both of these. Here are the results for Models 5 and 6. It seems that Model 6 is a better model than Model 2, although not by much. Now let's check model adequacy for Model 6. Based on the plots, we do have a standardized residual that is close to -3 just before 1930, but other than that, everything seems fine. The model that we chose was ARIMA 002X01212. We chose this model based on it having the smallest AIC. The model is adequate based on the diagnostic plots. Let's use the BJ techniques to find a model for the clothing data. Recall that we did this example when we looked at the seasonal exponential smoothing methods. We will use the first 10 years to create the model and the last year's worth for cross-validation. Here is a plot of the series. We already know that the series is not stationary from a seasonal standpoint. It does seem to exhibit some upward trend towards the end of the series. Let's look at the ACF plot from the seasonal perspective. The sample ACF plot indicates slow decay. This is what we expected to see. Based on the behavior of the sample ACF plot for the seasonal component, we can conclude that this series is not stationary. Since this data is monthly, let's try taking the first seasonal differences with S equals 12. Here is the sample ACF plot for the first difference series. It seems to be stationary. Now let's see about the non-seasonal piece. The sample ACF plot for the seasonal first difference series is given. This exhibits slow die-down behavior. We should conclude that this series is not stationary based on the non-seasonal component. Let's try the non-seasonal first differences for this series to see if it takes care of the problem. Based on the ACF of the new series, it seems that it does indeed cut off after lag 1. Even though there does seem to be some large sample ACF values at larger lags, remember that we expect this as we approach the seasonal lag. After taking the first differences from a seasonal and non-seasonal perspective, we get a stationary series. Now let's study the sample ACF and PACF from both perspectives to decide on a model. Let's start with the seasonal piece. Here is the sample ACF plot. It seems to have a large sample ACF value at lag 1 and 5. Let's check the sample PACF plot. This plot seems to die down. Based on the behavior of the plots, the seasonal piece exhibits AR4 behavior. Now let's look at the non-seasonal component. Here is the sample ACF plot for the non-seasonal piece. It seems to exhibit cutoff behavior after lag 1. Let's look at the sample PACF plot. Here is the sample PACF plot. It exhibits die-down behavior. Based on the behavior of the plots, the non-seasonal order for the model is MA1. So our potential model's choices become ARIMA 011X01112 or ARIMA 011X01512. Here are the model results. It seems that Model 2 is a better model. Now that we have data for validation, we should use it as another determining factor. Here are the forecasting results for Model 1. It seems that all of the actual values fall within the intervals. If this occurs with the next model, then we will use the interval widths to decide on our model. Also notice that the widths of the intervals get wider as the year goes on. Why is this occurring? The intervals cover the actual values for each month for this model as well. We will now compare the widths to decide. Based on the values for the widths, it seems that the widths for Model 2 are smaller for each month. Based on the smaller AIC and the fact that not only do all of the intervals cover the actual values, but the intervals are shorter as well, we will choose Model 2. Now we still need to make sure that Model 2 is adequate. Here are the diagnostic plots. Even though there are some extreme standardized residuals, near 3 in absolute value, the diagnostic plots don't show any reason to question the assumptions. We choose Model 2 because it fits best to the data and it is adequate.